So with that brief introduction to the kinds of registers and the architecture of the microprocessor, X86 microprocessor, let us look at the typical instructions that one might want to introduce in a microprocessor. So the instruction set is largely classified into these many kinds of instructions. Okay, one is you want to do data transfer, right? Or you want to do arithmetical or logical operations, stack operations, branching and looping, function calls, string instructions I'll do later, and then I'll also look at some idea of a prefix to instructions. So let us start with data transfer instructions. So typically I might want to move data from one register to another register, right? So the way it happens in x86, data transfer is always right to left. Okay, right to left meaning that the source register is on the right, destination register is on the left. Okay, and eventually after the data transfer, the source register is always unaffected. Okay, for example, if you say move EAX comma EBX, okay, whatever is in EBX first of all remains unchanged even after the execution of this instruction, but whatever is in EBX will get written into EAX. So the effective operation is EAX is equal to EBX after this operation is executed. Of course, EBX remains unchanged. So EBX has to come on the right, EAX comes on the left. So this move EAX comma EBX, right, is what we call a mnemonic or an assembly instruction. Internally, every assembly instruction will translate to a certain machine code, which is just a sequence of bits. In this case, it will be a 32-bit number, right? A 32-bit binary representation that stores something to tell you are moving data from EBX to EAX. Okay, it's a data transfer operation. You are dealing with EBX as the source and EAX is the destination. So something that encodes all this information will be available in the memory as a binary representation for this mnemonic or assembly instructions. You put a bunch of these assembly instructions together and then that's what we call an assembly program, right? Now I could also do something more interesting than this, right? For example, I may not want to treat the source register as data. I could choose to treat that register as an address, right? And therefore, I may want to move the contents of the memory location pointed to by EBX into EAX. Okay, so when you say move EAX comma EBX, right, effectively what this does, right? So if you do move EAX comma EBX. So in the mnemonic we use the square bracket to represent that we are talking of the contents pointed to by EBX. Then EBX is now treated like an address and the corresponding address bus will be populated with this EBX. Data will be read out from the memory onto the data bus and that data will be populated into my EAX. Okay, so that is very important to understand. On the other hand, when we did move EAX comma EBX, all we said was EAX equal to EBX. That means whatever data was in EBX was treated as data and that was simply written into EBX. This is purely an internal operation as far as the microprocessor is concerned. On the other hand, when we say EAX equals contents of EBX, it means this is actually going to the memory and getting you the contents of EBX. So EBX will first be put on the address bus, then you will assert the read, data will be read out of the memory onto the data bus, and then that information will get written into the register EAX. Okay. So here we are able to say that the data, that whatever the register is storing needs to be treated as an address and not data. Okay, so this is what we call the load instruction, because you are loading from the memory. Now I could do something more interesting than that, right? I could do not just treat the address as a particular, treat the register value as an address. I could say take the value from the register, add some offset to it, and then treat that as the address and get me the data from there, right? So when you say move ECX comma contents of EDX plus 4, this is also a load operation, but what we are now saying is we are moving the contents of the memory location pointed to by EDX plus 4 into ECX. Okay. So here I will say move ECX comma contents EDX plus 4. Then effectively we are saying this contents of EDX plus 4, right? Now what happens? It's very interesting because the processor, see now this plus 4, right, could be plus 8, could be plus 2, right? It depends. That is now whether I am doing plus 8 or plus 4 and all is actually part of this machine code. You are telling it to add an offset, a fixed offset, right, into this. Now what this is basically doing is it's reading the value of EDX, which is the register value, and then adding an offset, let's say using the ALU, okay, adding an offset of 8 to it, right, and reading, putting that value onto the address bus, reading it from the memory. That data bus is then written into ECX. Okay, this is what is, this value is treated as an address. It's important to note, I cannot do this particular operation, move ECX comma EAX comma EAX plus EBX. This I cannot do because I cannot say use EAX and EBX as two arguments, add EAX plus EBX, then treat that as an address and get me the value from that. Now that is not possible to do, right? It's not that it's impossible to implement this instruction, but the X86 instruction set does not allow this. So when you are dealing with a microprocessor, it is very important to understand the instruction set and understand what is allowed and what is not allowed. Okay. In the second half of the course, we will see why implementing such an instruction is futile. Even if you want to and you wanted to add it to an X86 architecture, it's not going to be very useful. So we'll come to that later, but definitely this is not possible. Okay. Right now, all we are saying is it can be a fixed offset, EDX instead of EDX. So for example, I could say move EBX comma ECX plus 4. That is possible. EBX will then get the contents of ECX plus 4, right? So in some sense, this is possible, right? But I cannot replace that fixed 4. That 4 has to be a fixed number, right? And that will get encoded into the instruction itself. That we will see a little later. Now, likewise, instead of loading data from the memory, I can also choose to store data into the memory. right? I could choose to store data. So what is storing? It is basically the exact opposite operation. So I can do store. Okay, what is store? I will say move contents of ECX comma EAX. This means that whatever contents of ECX is, treat that as an address and write the contents of EAX into that particular address. So the 32 bits from EAX register will go on to the data bus. Then you are going to treat ECX as the address, you will put that on the data bus and assert the write. So data will get written into the memory in this particular way. So likewise, just like we were able to add an offset, you can even do this thing here, move EDX plus 4, right? Move E comma ECX. So what will happen here implies you are doing EDX plus 4 equal to ECX. That is, you are taking EDX, adding a fixed offset of 4 to it, placing that on the address bus, then placing ECX, the value of ECX into the data bus and asserting the write operation into memory. So that's why this is called a store operation in the computer organization parlance, right? Exactly same rules hold even here. You cannot write, you cannot do move ECX plus EDX comma EAX. You cannot do this. This is simply not possible. It has to be a fixed offset. So whatever we discuss for load is also going to exactly hold for the store instruction as well. Okay. So there is also one more instruction called the load effective address, right? And this will kick in specifically when you are trying to do int y equal to ampersand x in C programming. Okay. So when you say LEA EAX comma EBX plus 4, right? So let us look at that. So this is a slightly different. This is not a load or a store operation. LEA EBX comma ECX plus 4, right? So this is a slightly convoluted thing to say EAX, or let me just use the same instruction as here. This you are effectively saying is this EAX equal to EBX plus 4. Okay, so this one is a, it's a slightly convoluted way of doing something which is very simple. In the RISC processors, this is done very trivially. Okay, so I will leave it at that. Just remember that if you want to do EAX equal to EBX plus some offset, right, then the only way to do that is through the LEA instruction. See, for example, I cannot do move EAX comma contents of EBX. So let me just, so there is a difference between move EAX comma contents of EBX plus 4 and LEA EAX comma contents of EBX. So here EAX is going to be contents of EBX plus 4. So EBX is read out, 4 is added to it, then that's placed on the address bus. It reads the data from that address and writes it into EAX. That is what happens in the move operation. On the other hand, the load effective address, it's a purely internal operation to the microprocessor. It does not even go to the memory. It is EBX plus 4 is just evaluated. The effective address, what we are trying to do in LEA is load effective address. What we are saying is calculate the effective address because of this operation, where if EBX was treated as an address and then you added 4. What is the effective address you get? You write that into my EAX register. Okay. So in some sense, this operation is getting the result of that intermediate addition that we are doing. Okay. So you could do even EBX -4 or -8. It doesn't matter. Okay. It's any of these things that are, you can do any of these offset calculations using this positive with positive numbers or negative numbers. But load effective address is getting the value of the intermediate address that has been evaluated that would have been used to access the memory had you done a move. Okay, that's how you should treat this particular thing. So again here you cannot do, for example, LEA EAX, EBX plus ECX. You cannot do this, right? This is absolutely wrong. It's not equivalent to saying EAX equal to EBX plus ECX. It's not possible to do this, right? So these are the things that you have to keep in mind and be very clear about what is allowed and what is not allowed by the instruction set of that microprocessor. Now the arithmetic and logical operations are of course exactly what you want to deal with. Okay, so I just showed you, for example, for a change here, instead of dealing with EAX, this time I am dealing with AX and BX. So I can do add AX comma BX implies, what is this operation? AX is equal to AX plus BX, 16-bit operation, right? Or if I said add EAX comma EBX, this implies EAX is equal to EAX plus EBX, right? So it is treating AX as one operand, BX as the other operand, and then replacing AX with the new value. Okay, so in some sense it is taking only 2 operands and treating one as the source, doing the addition, and then treating the one on the left as the destination register itself. Okay, so this is very important to understand, and of course the operation add will translate to the plus operation. Now you could do, just like we did move, you could also do subtract. What do I have here? AX comma contents of BX. So here, remember, like I told you, one of the operands of the ALU operations has to be a register. Okay, it has to be AX, BX, CX, DX, or it has to be EAX, EBX, whatever, one of these registers it has to be. The other operand could come from memory. That's exactly what we are doing here. So here we are saying AX is equal to AX minus contents of BX. So this operation is take the value of BX, treat it as an address, put it on the address bus, get that data from memory and subtract it from AX using the ALU and replace the value of AX with this new answer. Okay, so then I could do exactly, let's say for example, instead of subtract, I could do a logical OR operation, right? So I will say OR of AX comma contents of BX plus 4. Now this one is basically the OR logical operations, right? The logical operations in the X86 or in any microprocessor is typically a bitwise operation. So when I say OR AX is equal to AX OR contents of BX plus 4, right? It means you are going to go and get 16 bits of information from the memory. From which address? bx plus 4. Take the value of bx, treat it as an address, add 16 to it, put it on the address bus, get 16 bits from memory, and then do a bitwise OR operation on the AX along with AX and put the answer back into AX. That's what this whole thing means. So, when we say, for example, OR AX comma BX, right, this is basically going to say AX destination is AX or BX. What does this mean? It means AX of 0 bit, right, is equal to AX of 0 or BX of 0. Like that, for every bit, you do AX of 15 is equal to AX of 15 or BX of 15. Right, this is bitwise. This is a bitwise operation. So, all the logical operations that we do are indeed bitwise operations. Okay. And the addressing scheme, of course, carries over for whether you're doing ALU operations or move data transfer operations, right? You can take an address, you can add an offset, you can subtract an offset, whatever you want with it, right? Now, XOR, for example, there is an operation called XOR in X86. So, if I do XOR EAX, EAX, so it does not matter what value was originally in EAX. It could be some arbitrary garbage value, but after this, you will basically get the following result. EAX is EAX XOR, bitwise XOR with EAX. So, what is the answer? It doesn't matter what the value of EAX is, because XORing with itself will give you 0. So, this will eventually just set all the bits in EAX to 0, and it turns out this is the fastest way to actually clear a register.